seating settings. Okay, let's get started. So I mentioned I posted solutions to the exam on Lima. So please take a look, make sure that you figure out where you went wrong, and if you did go wrong, and ask questions if there are questions to be asked. Okay, so if there's something you don't understand, particularly something fundamental, make sure that you use the next couple of weeks to get it taken care of. We've got now roughly, we have 2 weeks and change in lectures. And so during that time, please do what you can to get caught up if you're not caught up. A couple of things. The average for this exam was extremely low. It's 34%. That is like a C minus, D plus, okay, just so you know. And so, you need to up your game, guys. Take a look at the answers and make sure that stuff makes sense, okay? The other point I want to make is that I get the impression sometimes people don't ask for help when they need it. I'll give you an example. We had a question and answer a week before the exam. How many people showed up out of 152? 2. That's like 1%. So, help is there for you, but you need to go get it. And so, you have time in between now and the final, do it. Okay, it's there for you. You have 4th hour by me. If you don't want to ask me questions, and I can understand that. Use the Learning Emporium, ask your TAs, but don't let it fester. I mean, this is what's happened. Look, there's no excuse at this late stage for people to not know very simple acid-base stuff, or for me to see that many pentavalent carbons. I shouldn't be seeing that stuff in Chem-273 at all, and I really should be seeing it on the last hour exam, right? And so, it's not the new material that's goofing people up. It's not having a good foundation. And as late as it is, you still can do something about it. So I urge you to. I sent out an email, in the sermon. So I sent out an email to the class yesterday with a list of problems for chapter 26, right? The numbering of the chapters changed a little bit, and going from 5th to 6th edition. And so we're going to cover chapter 26, which it has the same title and it covers the same material. It's the chemistry of aromatic heterocycles. And then after that, it's not chapter 27. In the 6th edition, it's chapter 28. And that is paracyclic reactions, and that takes care of it for the semester. So let's start with chapter 26 and try to remember what a heterocycle is. Well, cycle, okay, so it's a ring. We know that. And then a heterocycle just means it's a ring that has a heteroatom. A heteroatom is a non-carbon atom. So typically oxygen, nitrogen, oxygen and nitrogen, sulfur, sulfur and nitrogen, and so on. But not too many other atoms other than oxygen, nitrogen, and sulfur. And those are the common ones we'll see. Now, these aromatic heterocycles have been around for a while, and they have common names. As you well know, I'm not going to hold you to knowing the names, but we do want to familiarize yourselves with some of the simpler ones. So, chemistry of aromatic heterocycles. Pyridine is one we've seen. If you have 2 nitrogens, then pyrimidine. Pyrimidines, as you will see, are going to become important to us because this basic structure appears as the bases in nucleic acids. And so pyrimidines have a kind of a prominent role in biological chemistry. Quinoline and isoquinoline. We've seen quinoline as a catalyst poison, as you recall. Another place where you find quinoline is in quinine. What's quinine? Well, it's a naturally occurring compound. What's it used for? Does everybody know? It comes from the bark of the cinchona tree in South America. Isolated from, did I hear it?
It's an antimalarial.
You're right, it's an antimalarial. That's the first antimalarial. Regrettably, quinine, it has toxicity, and so it's not an ideal drug, and unfortunately the parasite has widespread resistance to quinine, so this is no longer particularly useful. But you'll notice the quinoline ring, quinoline, quinine, you'll see it embedded in here, right? So this is a substituted quinine. It's got 1, 2, 3, 4 asymmetric centers. Nitrogen here is asymmetric, right? Because it cannot invert. Indole is another very common aromatic heterocycle, and this is the correct. I showed you lysergic acid last time. There was a mistake in the structure. I apologize. I had the carboxylic acid over on the wrong carbon. So lysergic acid, you'll notice, is an indole alkaloid. So there's the indole ring. And then there are these simple monocyclic ones. Pyrrole, this is the one you're going to have to remember, furan and thiophene. Imidazole you should also remember. So the names and the structures for these and for indole you really should remember. Oxazole, as it sounds, oxazole, so oxygen, nitrogen, thiazole, and so on. Purine, again, this is the basic structure for a lot of nucleic acids. So purine and pyrimidine bases are the groups in the nucleic acids. And then benzofuran, benzothiophene, it's, furan, thiophene, but with a phenyl in there. Dihydrobenzofuran is the saturated compound. Remember I told you something when we talked about carbamates. I said that carbamates were insecticides and they were fairly toxic, and there's one called carbofuran that's been used in Hawaii by banana growers. This is, I can't remember the structure, so I had to look it up. This is carbofuran, so you can see the carbamate here, but also notice that this is a dihydrobenzofuran. It's got 2 methyls here, so this is the structure of carbofuran. Very simple molecule, right? No asymmetric centers. Very toxic. The oral lethal dose, LD50 in mice, is about 2 mg per kg. So if you're 60 kilogram adults, then that will be 120 milligrams, not a whole lot of carbofuran to kill you. LD50 is defined as the dose that will kill half of the mice. Okay, so that's how you define toxicity. Small numbers, bad. So 2 mg per kg is not nearly. I mean, it's not like a really powerful neurotoxin. This is a neurotoxin, by the way. But it's poisonous enough that if you're not careful with it, you're going to kill yourself. So that's why the Department of Ag insisted that people get certified before they use it. So, pyrrole, 1 nitrogen, furan, 1 oxygen, thiophene, 1 sulfur, imidazole, 2 nitrogens, indole, and these are the ones you probably should remember. Now, I've said that these are aromatic heterocycles, so we need to remember a few things about aromaticity, which we've forgotten. And so in order for a ring to be aromatic, it has to be planar. Okay, so that means that the orbitals overlap all around the ring. There has to be an uninterrupted circuit of sp2 hybrids, and then finally it has to fulfill the Hückel rule. And the Hückel rule, remember, was that you had to have 4n plus 2 pi electrons, and where n is an integer, so either 2, 6, 10, and so on. And so now we need to remember how we count electrons. So I'm going to remind you of something that we have talked about before, but perhaps you've forgotten. And we're going to illustrate that with pyridine on the one hand, electron pair, and with pyrrole on the other. Okay? So pyridine and pyrrole, and so I have an electron pair of nitrogen in both cases. Now the electron pair here is a vinylic electron pair, because the nitrogen is sp2 hybridized and has a double bond. Here, the electron pair is not vinylic; it's allylic. You can see that the electron pair is in the allylic position with respect to each of these alkenes. Allylic electron pairs count, and vinylic electron pairs don't count. And when I say count and don't count, I'm talking about the Hucke rule for n plus 2. Now the reason for that is simple. The vinylic electron pairs are within the plane of the ring, and so those electron pairs don't overlap with the ring. The allylic electron pair, on the other hand, is in an orbital that overlaps with the others. So both of these compounds are, for Hucke rule purposes, 6 pi electron compounds. So these have 6 pi electrons. It fulfills that rule. You don't count these because these are vinylic, so 2, 4, 6. You do count these, 2, 4, 6. So both of them are 6 electron aromatic compounds. Okay? So, one more time. Vinylic, you don't count those for the Hucke rule purpose. Allylic, you do count those. Okay. So, if we go back to imidazole, let's take a look at imidazole, because both of these nitrogen atoms have electron pairs. This is, however, a 6 pi electron system. Why? Well, because this electron pair doesn't count. That's vinylic. This electron pair is allylic. That one does count. 2, 4, 6. 6 pi electrons. Okay? And so that's how we can count these up. Okay, so structure and aromaticity. Let's change the sequence just a little bit. So when we talk about aromatic stabilization, what are we talking about really? Well, we're talking about some special stability that an aromatic compound has that doesn't seem to fit the pattern of alkenes. So remember when we first encountered this concept, it was with benzene. We said that, well, benzene looks like a polyene, it's a triene. How come when I just take bromine, typical alkene reaction, in the absence of any kind of catalyst, nothing happens. Benzene just sits there and it doesn't react with bromine. You take cyclohexene or cyclohexadiene, you add bromine, instant reaction at room temperature. Something's wrong, something's different. And the difference is that unlike cyclohexene, unlike cyclohexadiene, benzene is aromatic, which means it's between 33 and 36 kcals per mole, more stable than it should be. Well, what does that mean? Well, it means that it is more stable than what you would expect for an alkene that was not conjugated. And we defined that before, it was not aromatic. And so it doesn't matter whether it's 33 or 36, this is a big number, okay? And so that explains why the reactivity is so low. Pyridine, less aromatic stabilization. Thiophene, less yet. Then once you get to furan, you see you're at 16 kcals per mole, so it's still aromatic, but big difference in stabilization between these two and that one. And so you can imagine that these two aromatic heterocycles are going to be what? They're going to be much more reactive than benzene, and that's borne out. So a lot of the electrophilic aromatic substitution chemistry that we saw for benzene, sure, it works for these heterocycles, but the ones that don't have particularly large aromatic stabilization, those react really fast and sometimes in the absence of catalyst, okay? So yes, they are aromatic, but they are not nearly so unreactive as benzene. These are actually fairly reactive compounds. So now let's take a look at the structures. So if we look at furan is the one that has the oxygen. then I can write all of these resonance structures for furan. And the first one, of course, is going to be the most important because I have no charge separation. In each one of these resonance structures, I've taken a plus charge and a minus charge and I've pulled them apart. Now that costs you energy because of Coulomb's law, and so you know already that these resonance structures are going to be less important than that, and this one will be less important than this. Why? Well, because I have a larger separation between plus and minus charge, smaller separation here. But these are the resonance structures that I can write for furan. Now, these resonance structures have an effect on the dipole moment. And so if you compare just tetrahydrofuran, the reduced compound on the left, it has a dipole moment that's fairly substantial, 1.7 divide. You compare that with the dipole moment of furan on the right, and that's much less. Gee, how come? Well, okay, so let's start, and oh, by the way, and the dipole moment is reflected in the boiling point. Lower boiling, because you don't have a strong interaction between the molecules, plus and minus. Stronger interaction here, and so you can see big difference in boiling point. Now, why is this one polar? Well, because of the usual reason. You have an electronegative oxygen atom. The electronegative oxygen atom is bonded to carbon. Carbon is less electronegative, so those are polar covalent bonds with the plus end on carbon and negative end on oxygen. And so if I sum up the two vectors, the two pink vectors, then I end up with a net dipole that points in this direction. And I have that same kind of dipole here, like that, but if I go back to the resonance structures, you'll notice that there's another dipole with a plus end on oxygen and a negative end on any of the carbons. And so each one of those resonance structures has a dipole moment pointing in the opposite direction. And so I take this dipole and I add it to those other small dipoles, and what I end up with is a relatively smaller overall dipole moment for the tetrahydrofuran than I otherwise would have expected. And so this is a pretty good indication that we are getting, that those resonance structures have some validity. Okay, so you should be able to write resonance structures for any of these aromatic heterocycles and get some insight for the reactivity. So let's do this for pyridine. So the two important resonance structures, just like benzene, are going to be the ones that have no charge separation. And so these two are equivalent, no charge separation. These are going to be the important ones. And then I have these three where I do have charge separation. And these will be less important than the others, but these will give me some insight to the reactivity of pyridine, as we will see. So, a lot of these heterocycles, as you've seen, are amines, right? So they're aromatic amines. Now, when we have aromatic amines like pyridine, we've noted in the past that these are bases. Okay, so any nitrogen atom that has an electron pair should be to some degree basic. This is basic. And so I can take the pyridine, I can protonate it, and you'll notice that this is a reasonably strong acid. It has pK of 5.2, which means pyridine is not a super strong base. It is almost 100,000 times less basic than triethylamine. Triethylamine is a very much weaker acid, the ammonium ion, much weaker acid than that, which means this base, triethylamine, is about 10 to the 5th more basic than pyridine. And you'll notice that the difference in basicity between these two amines, as judged by the pK of the conjugate acid, is not substantial. It's 3/10 of pK unit. So whether I have quinoline or pyridine, not particularly strong bases. Aromatic amine, not a strong base. But the triethylamine is. And so this is due to the fact that you have a different hybridization of the electron pair in the aromatic amine versus the aliphatic ones. The aliphatic amine, the non-bonding electron pair that bonds to the proton, is in an sp3 hybridized orbital. It's an sp2 hybrid here, and the sp2 hybrid is lower in energy, and so that's reflected in this really stark difference in basicity. It's not to say these are not basic; they are clearly. Certainly, they're basic with respect to a very strong acid like HCl or HBr, but they're not particularly strong bases, the aromatic ones. Now, we talked about pyrrole here. Okay. And we said, you know, that electron pairs and whatnot. Now, we just saw that the pyridine undergoes protonation of nitrogen. And so it would be completely reasonable, if you didn't think about it, that is, to expect this to happen, where this electron pair picks up a proton. So if I allow the electron pair to pick up a proton, I would expect to form that ammonium ion. And so this ammonium ion actually does not form. You don't get that. And so why is that? Yeah, it's not aromatic. And so you lose aromaticity when that happens. So as a result, when you protonate pyrrole, protonation takes place on the ring. And this is something that, you know, at first glance seems a bit surprising, but then when you think about it, of course it makes perfect sense. You don't want to lose the, you know, the 20 kcals per mole aromatic stabilization, and so protonation takes place at the alpha carbon to give you this stabilized cation. Now, you could say that, well, you know, you've lost aromaticity here, yes, but at least the cation that you end up with is resonance stabilized, whereas the one that I showed before is not. And so this cation is going to be more stable than the other one, even though you have lost aromatic stabilization. The other case, you lose the aromatic stabilization, but you don't get anything back. Here you lose aromatic stabilization, at least you have a stabilized cation. Now, notice that the protonation takes place at carbon atom 2, right there, and not at carbon atom 3. And so the question you might have, should have, is how come? Why is it that I don't get protonation at carbon atom 3? The answer to that is because if I do, I end up missing one of these resonance structures. So you need to convince yourselves of that. So if I show protonation taking place at this carbon atom, then then I'll end up with that cation, for which I can, for which I can only write a single resonance structure, right, or two resonance structures. So in this case, two resonance structures. I can't delocalize that positive charge to any of the other carbon atoms, whereas with C2 protonation, I get three resonance structures. Less stable cation, this doesn't happen. Protonation takes place at C2. Same thing, by the way, for thiophene and for furan. And so, yeah, not surprising. This is the way we always figure out what happens, right? We look at the conjugate acid and see how stable is it. Conjugate acid, here's that cation. We figure out how stable it is just by counting up the resonance structures, and it's the same drill. Now, pyrrole is also, it also has an NH bond, right? So if I look at pyrrole, it has this NH. Now, we've seen before that amines are amphoteric compounds, just like alcohol. So they can be acids, but they will react with bases, through strong bases. So with a strong base, I can pull off that proton. But that's going to require a fairly strong base because the pKa of pyrrole is about the same as ethanol. A little bit, 1 pKa unit higher, so just a little, 10 times less acidic than ethanol. So if I allow the pyrrole to react with a really strong base, like methyl grignard, so think of methane as having a pKa of 55 or 60 or whatever, so a huge difference, then that proton gets pulled off, end up with methane gas, and end up with a brommagnesium anion of the brommagnesium salt of pyrrole. And that negative charge, notice, is going to be delocalized into the ring. And so you can write another resonance structure here. So this proton is not especially acidic, but it's like think of it like sort of like an alcohol. So that means that pyrrole can react with acids or with bases, strong bases, however. Now, why make a big deal about heterocycles? I mean, there's a separate chapter here, and you might ask yourself a question. Well, it seems like kind of a little bit esoteric. And in one case, in one sense, you're right. It is a bit esoteric, but not in the other sense, because aromatic heterocycles play a dominant role in nucleic acid chemistry, but also aromatic heterocycles are present as substructures of just about all the drugs we use. Okay, so when you go to the pharmacist and you buy something for whatever, chances are it's going to be an aromatic heterocycle. Those substructures appear in the vast majority of pharmaceutical agents, maybe 80%, maybe more, I don't know. But so they do play a very important role, and that's why we talk about them. Now, having said that, the chemistry is easily understandable based on first principles that we've discussed. However, the chemistry is also a little bit idiosyncratic, as you'll see. So there's some kinds of reactions that aromatic heterocycles undergo that seem just a little bit different, but you can understand them from first principles nonetheless. Okay, so let's take a look at reactions of furan, pyrrole, and thiophene. And since they are aromatic, we should look at something we've seen before, which is electrophilic aromatic substitution chemistry. Now, we spent a lot of time talking about this. We talked about it again recently in the context of diazonium ions. And so now it's coming back to us another time. And so recall what I said about aromatic stabilization of these three species. They are all aromatic, but much less stabilized than benzene, which tells us what? It tells us that in terms of electrophilic aromatic substitution, these are going to react much more rapidly, much more readily. So let's start out with furan. Notice that I'm using acetic anhydride as the electrophile with BF3 ethering. Now, when I did and this, by the way, is what? It's a Friedel-Crafts acylation reaction. Now, recall that when I tried to do a Friedel-Crafts acylation reaction with benzene, what did I do? I had to use acetyl chloride and aluminum trichloride to get a really reactive acylium ion as my electrophile. Here, I don't need to use an acid chloride. I can use the much, much less reactive anhydride. Because why? Well, because the furan is more reactive. And I end up getting a very good yield, as you can see, of the C2 acetylated compound. So we'll talk about positional selectivity in a minute. And if I do an aromatic nitration using nitric acid, I don't have to use a strong dehydrating agent. I can just use acetic anhydride as the dehydrating agent. And I get overwhelmingly C2, but a little bit of C3 nitration as well. Now, why is it that I see a preference for C2 over C3? I don't get any C3 here, none. Here I get just a tiny bit. The reason, as usual, is to be found in the stabilization of the charged intermediate that you get. So it's Hammond's postulate. The charged intermediate, shown here, is stabilized by those same three resonance structures that I showed for protonation. If I show acylation at C3, which I will do in a second, then I only get two resonance structures, implying that that particular site is going to be less reactive than C2. And so this is the important resonance structure because everything's got knocked dead. But I end up with three resonance structures for C2 acylation. Nitration would be the same thing, obviously. In fact, any electrophile is going to give me these same three resonance structures for acylation, nitration, whatever, at C2. Now, at C3, you only get two resonance structures. And so one fewer. So if I take a look at what happens when, in this case, acylation takes place at C3, these are the only two resonance structures. It was exactly the same situation that I showed you for protonation, same thing. And so C3, no go. Okay, so the relative reactivity of these compounds is shown here with respect to benzene. So if we say that the rate for benzene, if we assign that an arbitrary rate of 1, then the rate for thiophene is going to be 5 billion times faster. And look at how much faster pyrrole is. So these are extraordinarily more reactive in electrophilic aromatic substitution reactions than benzene. And so that tells you that doing electrophilic aromatic substitution, particularly for these two, is going to be much, much easier than the hard job we had with benzene. So these electrophilic reactions are conducted always under much milder conditions than we saw for benzene. Now, having said that, the increase in reactivity can be problematic. It can be problematic for the following reason. Let me see if I can explain this to you in a way that makes sense. So let's just say that I have and I really don't care whether it's oxygen, sulfur, or whatever, but this is going to be the biggest problem when X is NH. When X is NH, I have the highest reactivity, right? That's compared to benzene. So let's just say that I allow this to react with some electrophile, generic electrophile, okay? And so you know already that what's going to happen is I'm going to end up with this as an intermediate, okay? And I'm not going to show all of the resonance structures. Now this is a cation. This is a cation too, isn't it?
Yes.
So I have two electrophiles. This is also electrophilic. So in the presence of a very reactive aromatic like this, guess what can happen? This can react a second time. So this can act as the electrophile towards another heterocycle. So I can get multiple addition. This reaction generates another cation. If there's still unreacted heterocycle, that can be intercepted. And again, and again, and again. And what does that lead to? That leads to a polymer. And usually, nothing good. Usually when that happens in your reaction, you end up looking at it, seeing a black tar that won't dissolve in anything. So you get this black, hard stuff you got to chip out or throw the flask away. And so you need to shut down this process by either using mild conditions or dilute conditions in both. Otherwise, this huge reactivity, especially for pyrroles, gets in the way of what you want. So yeah, so they're reactive, but that of course means that you have to take that into account. There's a problem at the end of the chapter that asks you to consider exactly this reaction of pyrrole reacting with a cation at the end of, yeah, it's one of the assigned problems. Okay, now when we talked about electrophilic aromatic substitution chemistry in the context of benzene, remember what we said. We said that if I have an electron donor group, And donor groups were electrons donating because typically they had, it was either an alkyl or it was an oxygen with an electron pair or something like that. That these were ortho-para directly. And if I had, on the other hand, if I had an electron withdrawing group, something like a nitro or sulfone or an acetyl, these were meta-directing. That meant that if I did an electrophilic aromatic substitution on this compound, I would see reactivity at these positions. Those are the two ortho and the para. If I did an electrophilic aromatic substitution on here, I would see reactivity there and there. Okay? So this was the selectivity, the positional selectivity that we discussed way back when. So now it comes up again in the context of this aromatic heterocycle business. And so the easy way to look at it is this. I'll illustrate this with oxygen. So what I'm going to look at is I'm going to look at ortho-para, meaning here and there. So that would be ortho-para substitution. And meta will be there, okay? And so let's see how this works. So another way of looking at it is say that W groups will direct 1, 3, and donor groups will be 1, 2, and 1, 4. And the other thing you have to remember is that the heteroatom, oxygen, nitrogen, sulfur, always directs at C2. So it doesn't matter, nothing else matters, but these two positions are always going to be activated by the heteroatom, these two. So now the question is, how about the others? Well, it's the same situation that we have, where you have maybe reinforcing or opposing effects, right? And so if I have a reinforcing effect by a prior substituent, then I'm in good shape. And if not, then I end up with a mixture. So let's take a look. Okay, so let's start out with thiophenol carboxylic acid. And this is going to direct meta. So it directs here. And sulfur also, well, sulfur directs at both of these carbon atoms. But this position is the one that both the electron withdrawing group directs and sulfur directs. And so you end up seeing exclusively the product at that position. You don't see any of bromination at this site. Notice, by the way, the conditions, bromine and acetic acid. So I don't need to use ferric bromide or any kind of strong Lewis acid to activate that process. That process takes place under extremely mild conditions because why? Because the thiophene, even when it's substituted with the carboxylic acid that is electron withdrawing slightly, is still reactive enough to react with plain old bromine. So here the two directing groups, the sulfur and the carboxylate, reinforce each other. Okay? Now, if I do it the other way, if I take a nitro group, also electron withdrawing, that's going to direct to the meta position. The sulfur directs at the ortho position. So now I have a conflict. The sulfur directs here. This position, of course, is blocked, so we don't need to worry about that one. And so, predictably now, I end up with a mixture of products because the two directing effects, the one from the sulfur and the one from the nitro group, oppose each other. Now, if you have questions about why the nitro group directs where I said, then what you need to do is you need to write the resonance structures. And as soon as you do, it'll make perfect sense to you. Remember what nitro groups do. They pull electron density out of the ring, and so the resonance structure you never want to see is the one that places a positive charge on the same carbon atom that bears the nitro. So that is the resonance structure that is the least stable and the one that is not going to contribute to the reactivity. On the other hand, Chlorine, although it is slightly deactivating, is orthopara directing. So it directs to this carbon atom and that one. And so sulfur, on the other hand, directs here. So this position is where both sulfur and chlorine direct. And so nitration takes place essentially exclusively at this site, and you don't see nitration there. Now, if it goes without saying that if the activated site is blocked, then you do get reactivity at the unactivated site. So if it has no choice, I mean, here both of the positions that are activated strongly by the oxygen, they're methyl groups, so no chance of acylating here or there, not at C2, not at C5. And so if it acylates at all, it's going to acylate at C3, and that's what you see. So it's pretty much the same chemistry that we've seen all along with electrophilic aromatic substitution. You can understand it just the way we did with benzene by writing resonance structures for the charged intermediate that you get. How do you know where the electrophile is going to attach itself? It will attach itself to the carbon that gives rise to the most stable cation. And you know what determines cation stability. You know how to write resonance structures, so you can always figure it out. Now, remember that furan had only about 16 kcals per mole aromatic stabilization. And recognize that furan has a structure that a structural feature that we've seen before. If I ignore the oxygen atom, then this looks like a conjugated diene. And so even though it is aromatic, it only has 16 kcals per mole stabilization, and so it's maybe not too surprising that furan will react like a diene sometimes. And so it has some diene-like activity. Now, what is the quintessential diene reaction? The reaction that, dienes undergo, no other species undergoes that reaction. That's the Diels-Alder reaction. And so furan will participate in Diels-Alder reactions. And so if I take a molecule, furan and a dienophile, dienophiles, remember, are alkenes that are substituted by electron withdrawing groups. So maleic anhydride is a good one. And I heat them up. I end up with a concerted cycloaddition reaction that forms these two red bonds. And I end up with this Diels-Alder product in greater than 90% yield. Now that is not the kind of reaction you expect to see from benzene. So Diels-Alder reactions of benzene don't in general occur. There are very few small exceptions to that. We don't need to go through those. But in general, benzene doesn't do this because why? Well, because benzene is too stable. Once you do this, any aromaticity is lost. And so then you can say that, well, then why does it happen? Well, it happens because sigma bonds are strong bonds. And so I'm exchanging 2 pi bonds, this one and one of these two, for 1 pi bond and 2 sigma bonds, and the loss of 16 kcals in aromatic stabilization is still lower in energy than these two. So, bottom line, furan and also thiophene and also pyrrole will participate in Diels-Alder reactions. Another reaction that dienes do is conjugate addition. And remember that we had that business of adding either HCl or bromine to a conjugated diene and then figuring out what the product is going to be. And well, the same kind of chemistry takes place actually with furan. So if I treat furan with methanol and bromine, you end up getting a bromine, the positively charged cation, and then that gets attacked by methanol to give you the 1,4 adduct in very good yield. And this chemistry is very easy to do. So you don't have to heat it up or anything. You just add the bromine and methanol and bang, it reacts. And furan in particular, but also pyrrole will do this kind of chemistry. Both kinds of reactions are trickier with pyrrole because pyrrole is very reactive and does this polymerization business we talked about. But doing this kind of chemistry with furan is actually quite easy. Now, there were other reactions that we talked about when we talked about aromatic chemistry. There's some reactions that were characteristic of benzene. And one of them was reactions that took place at this position, the benzylic position. And recall that I could do a couple of things there. I could either form a radical using radical reaction conditions, an initiator and whatnot. I could do specific brominations, that benzylic carbon atom. The reason I could do that was because the benzylic radical was resonance stabilized. Or I could do oxidative chemistry. I could oxidize this with a strong oxidant all the way to the carboxylic acid. So side chain chemistry is something we've seen in our earlier discussions. Now, it turns out that side chain reactions work also with furan, and some of these are a little bit easier to do than with benzene. So it turns out that we can decarboxylate furan fairly easily. This is an important process industrially, by the way. So this kind of decarboxylation is quite useful. Side chain oxidations, you can do those too. You can take the side chain either as the aldehyde or as the alcohol and oxidize it all the way to the carboxylic acid. Doing benzylic halogenation and whatnot, that also works with heterocycles. So the bottom line is that the chemistry of these aromatic heterocycles doesn't look that much different than what we've seen before. You can understand it based on first principles. It's a good time to go back if you've forgotten the business about writing resonance structures for the charged intermediates for benzene electrophilic aromatic substitution. This would be a great time to go back and review that. And although some of the chemistry that we talk about in this chapter seems a little bit peculiar, it is all understandable based on first principles. Okay? So we'll pick up our discussion on